Periodicity 2, transitional model. Transition metals, part 2, coloured complexes. Essential idea. The d orbitals have the same energy in an isolated atom, but split into two sublevels in a complex ion. The electric field of ligands may cause the d orbitals in complex ions to split, so that the energy of an electron transition between them corresponds to a photon of visible light. Nature science, models and theories. The colour of transition metal complexes can be explained through the use of models and theories based on how electrons are distributed in d orbitals. And there's a bit of a transdisciplinary thing going on here, because the colour that's linked to symmetry can be explored in the sciences, but also in architecture and in the arts. So transition metal compounds are coloured, and the compounds containing transition metal ions typically have characteristic colours. For example, titanium 3+ is kind of a purple colour, vanadium, vanadium 2 is kind of purple, vanadium 3 is green, vanadium 4+, blue, vanadium 5+, yellow, etc., etc. So they have their own unique colours, typically. There are exceptions. In the first row, D-block elements, scandium and zinc. These compounds only form colourless solutions, and you'll be expected to explain why. So why do transition metal compounds have these colours? Well, the colour is related to the presence of partially filled d orbitals. And if you have a look down there, you can see almost a rainbow on the right hand side from violet, green, pink, yellow, green and blue. And you can see we're going from scandium to titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc, going right along there with a full range of colour. Well, we need to know a bit about colour theory first. Colours opposite each other are called complementary colours, and you can see this on the colour wheel. Okay, if you look at the colour wheel, there's this one that isn't in colour. You can see that the colour wheel shows the colours according to their wavelength here. So you've got the lowest wavelength starting with violet, and it goes around blue, green, yellow, orange, getting longer until it gets to red. Okay. Complementary colours. The complementary colour of red is green. The complementary colour of violet is yellow. Okay. Coloured chemicals absorb some of the colour, the wavelength of light, and you see the colour that is transmitted through or reflected off the substance. So you don't see the colour that's absorbed, you see the colour that's opposite the one that's absorbed. So if green was absorbed, you'd see red. Okay. The transmitted colour is complementary to the colour absorbed. So a substance absorbs green, it will appear, it's going to be red, isn't it? And a substance absorbs light with a wavelength of 615. What colour will it appear? Well, 615, find it, it's going to be, it's absorbing orange, so it's going to be blue. Let's have a look. Potassium chromate is yellow. Okay. So if it's yellow, it is absorbing a violet light with a wavelength of between 400 and 424. So between 400 to 424. And something really interesting happens to this d sublevels in the presence of ligands. There's splitting of d orbitals. The isolated transition metal, so when it's on its own, the atoms have d orbitals with the same energy. Okay, these are called degenerate orbitals. They all have the same energy. Degenerate means they all have the same energy. The d orbitals in the transition metal ions in compounds are split into two energy levels. Okay, and you can see this on the right. the 1, 2, 3, 4, 5 orbitals there split into 3 and 2, and there's an energy difference between them. The energy difference, delta E, corresponds to the region, to the visible light region, and that's how you see these colours. So when the d orbitals are split, an electron in the lower level can be excited when white light shines on the substance. The electron absorbs a photon of light with an energy equal to delta E and moves to the high energy level. So imagine light coming in, hits the atom, and the electron, which would have been here, moves up, it gets boosted up to here. So the electron is absorbing a photon of light with an energy equal to delta E. This is what moves it to the higher energy. The substance has a colour that is complementary to the colour absorbed. So whatever colour is absorbed, you see the complementary colour. If you recall, we've got these 5 shapes to the d orbitals. And these 3 at the top lie between the axes. So you can kind of see that if you've got your axes X, Y, Z here, the orbitals are between the axes. Okay. However, the other one, the dx squared and dx squared minus y squared, the d orbitals lie along the axes, so you can see the orbitals actually on the axes here. Okay. In a free ion, all the d orbitals have the same energy, and so all sit like this here. Degenerate. Let's have a look at this copper complex. Water ligands form coordinate covalent bonds with copper ions to form this copper complex ion. This hydrated copper ion is octahedral, and the water ligands lie on the X, Y, and Z axes. The lone electron pairs on water repel the d orbitals lying along the axes, causing the d orbitals to split into 2 different energy levels. So let's have a look here. So we had the free metal ion. As the ligands approach, you're getting a boost in energy, which then splits into 2. The higher energy levels are the orbitals which lie on the axes. You can see here, it's probably more clear. This is lying directly on the axes. The lower energy level orbitals are the orbitals that are between axes. When white light falls on the complex ion, the d electrons can absorb an energy equal to delta E. So the transmitted colour is the complementary colour of that which is absorbed. Let's have a look here and see if we can fill this in. We've got wavelength absorbed here 500. We need to find the colour absorbed and the colour of the substance. So 500 nanometers is going to be between 491 and 575. It's going to be green is absorbed, and red is transmitted or reflected. Green, red. The next one, we've got 620 nanometers. So 620 is between 585 and 6475. So it's going to be orange, and it's going to transmit blue or reflect blue. Next we've got 420. 420 is nearly getting on the blue, but it's still in the violet area. So it's absorbing violet and it's transmitting yellow. And this last one, we have we're given the colour. We know that it absorbs blue. So absorbing blue is going to be somewhere between 424 and 491. Let's just say 450, shall we? And then obviously it's going to transmit orange. There we go. Some of the factors affecting colour of transition metal complexes. The colours of the transition complex depend on the energy difference, the delta E, between the split d orbitals. And there's 4 factors that affect the value of delta E. There's the type of transition metal, there's oxidation number of the transition metal, or the charge on the metal ion, the type of ligand, and finally the geometry or stereochemistry of the complex ion. The 4th one we're including, but we'll only really need to look at the octahedral complexes for IB chemistry. So the effect of transition metal type on d orbital splitting. The number of protons in the nucleus changes, obviously, as you go from one transition metal to the next. The strength of the force of attraction therefore changes between the metal ion and the ligand. So the higher the nuclear charge gives you a more effective ligand interaction, which gives you a higher change in energy, and a higher change in energy gives you absorption of light with a shorter wavelength. And this can be seen here. You've got this manganese complex, which is pink. Manganese 2 plus has 25 protons, and it absorbs green, which has got 55 nanometers wavelength. And then you've got this iron complex, which is an orange-brown colour, Fe3 plus. It's got 26 protons, so it's got one more proton. It's still 3d5 though, and it absorbs blue, so it's absorbing light with a shorter wavelength because it's absorbing light with a higher, because there's a higher energy difference between those d orbital levels. Effective oxidation number on d orbital splitting. The number of electrons in d sublevel is different. This affects the strength of the force of attraction between the metal ion and the ligand, as you'd expect. The increased oxidation number gives you increased splitting, which gives you an increased difference in energy. The increased energy means that you're absorbing light with a shorter wavelength. This chromium complex, the blue-green colour, chromium 2 plus, has 22 electrons, and it absorbs red with 680 nanometers. This chromium complex, which is 3 plus, is violet. It's got 3 plus, and it's got 21 electrons. So it absorbs yellow with 560 nanometers. Again, you can see it has, because the chromium 3 plus is has a bigger split between the d orbitals, it is absorbing light with a shorter wavelength. The effective ligand type on d orbital splitting. The ligands have different charge densities. This affects the strength of the force of attraction between metal ion and the ligand. The higher the charge density, the more effective the ligand interaction, the higher the split in energy. Therefore, it absorbs light with a shorter wavelength. This copper complex is turquoise with water as its ligand. Water has a low charge density, or fairly low, so it's going to absorb orange. Whereas this copper complex has ammonia as its ligand, which ammonia has a larger or a greater charge density, and it absorbs yellow, so it gives this deeper blue colour. The effective ligand type on d orbital splitting continued. You can see this spectrochemical series in this box here. You can see that iodine gives the smallest amount of splitting of this collection, followed by bromine and chlorine. Water's in the middle there, and you've got the nitrile and ammonia giving the greater d orbital splitting. Look at these graphs here. You can see with just water as the ligand, you've got on the spectrum the peak at a higher wavelength than you do when we've got some ammonia as ligands, and you've got the peak a bit lower down. Okay. Water has a lower charge density, therefore less splitting. It's got a lower delta E, and that means it absorbs a longer wavelength. Ammonia has a higher charge density, so you get greater splitting because the higher delta E sort of absorbs a shorter wavelength. Finally, the effective geometry on d orbital splitting. This is really just for your information. Recall, coordination number is the number of ligands bound to a metal ion. The shape of a complex ion changes the way the d orbitals are split and the delta E value. Here, you have a tetrahedral copper complex. And in the tetrahedral copper complex, the d orbitals split in a different way. You can see here that instead of z squared minus y squared being above the other orbitals, as is in the octahedral splitting, they're actually below. And the difference between the two levels is a lot smaller, which will give a longer wavelength. Here, as we have already talked about, the splitting is as so, with the orbitals that go along the axes higher up, and there's a bigger energy difference between them. Bigger energy difference, lower wavelength. Okay, that's it, and it is in fact Christmas Day here, so Merry Christmas.